before we move on to the idea of vector functions and space curves, let's first just talk about functions in R2. Um, just as a reminder to get you thinking in terms of functions here, the way we define functions in R2 is basically we had a domain, which we think of as, x1, x2, up to xn, and we have the range, y1, y2, out to yk, where n and k do not have to equal each other. And we think of a function, say f, as a box, some type of machine. You take a value from the domain, it goes into machine, it works its magic on it, and out comes a value into the range. So that's the basic idea behind a function. And we look at functions, definition of functions in R2, such things as being one-to-one and that sort of a thing, passing a vertical line test, and look at the horizontal line test for inverse functions, and so forth and etc. And notation-wise, we think of like f of x being a function of x equals, something. How about x squared plus 3 or something, whatever. So in general, this is the basic idea of a function. It has a domain. The function itself is a rule of some type, and that rule takes values from the domain and maps it to the range. Well, that same idea, that same general idea applies to a vector function. A vector function is simply a function whose domain is a set of real numbers, which is the case in virtually all the functions that we've worked with. The domain here is typically real numbers. And the range in R2 is also a set of real numbers, but the range in vector functions is actually a set of vectors. So the domain is real numbers, but the range is actually a set of vectors. Now, we are typically more interested in vector functions whose values are three-dimensional vectors. We're typically working in 3 dimensions when we're dealing with vector functions. Now, we write r of t, which r is obviously a vector. Now we're writing this vector as a function of t, equals, in component form, f of t, g of t, h of t, which I can write as f of t I plus g of t j plus h of t k. Let me fix this one. I don't like the way I wrote that. Okay, g of t j. There we go. So we can write this vector function in either form, because quite frankly, sometimes this form is a little bit easier to work with. Sometimes this form is preferred. Now, when we write our vector function out like this actually means for every value of t, such that f of t, g of t, and h of t are defined, f, g, and h are real valued functions, and we refer to them, or we call them, the component functions of the vector R. Now, we use t as the independent variable typically because it represents time, and in most vector function applications, we're probably dealing with time. Now, consider r of t. Obviously, r is a vector function, equals the square root of t. Let me write it in. There we go. 1 over t squared. So obviously I'm in R3. And let's think about the domain here. What is the domain of R of t? Well, I'm going to take each component and look at the domains for each individual component. First of all, we take a look at the square root of t. Square root of t is defined on the interval 0 to infinity. Or we could write t such that t is greater than or equal to 0. However you want to write it. 1 over t, that's defined for all t non-zero. And obviously t squared is defined for all t, for all real numbers. So in terms of the domain now for this particular vector function, I need to take a look at each of these domains, the domain for each component, and the domain for the function will be where this domain overlaps. And where that overlaps is the domain for R of t will be 0 to infinity. We can't include 0 because of this guy right here, obviously. So that's going to be our domain for the function, or for the vector function. And we could write it, I suppose, as domain equals t such that t is strictly greater than 0. That'll work.